Hey, howdy everybody. Last time we were talking about principal component analysis for the purpose of dimensional reduction and also for inference, learning about the structures within our data. And we also introduced the idea that we could make predictions using principal component analysis in order to do a regression type of a model. And so we discussed that. Now we're going to get into the decision trees, which is an opportunity to talk about quite an understandable methodology for making predictions with machine learning. And so let's go ahead and get started. Now, if we're going to talk about working with a model based on machine learning, we should probably cover a short discussion or review from a previous lecture on training and testing. And so in general, you'll find that we have data available for fitting a model, but we don't want to take all of that data and apply it to fit the model all at once. Because if we do that, then we don't really know how our model performs. And in fact, we probably could be guilty of overfitting. We've we've set some type of parameter, so we minimize the error in the model, and then we'll do very poorly away from the training data at new information. So we want to have two phases when it comes to building our model. We're going to have training and testing phases. For the training phase, we're going to retain a subset of the data, and we're going to use that in order to select the model parameters to fit the model. And this will be based on optimization, usually to minimize mean squared error or residual sum of square error or some measure of error. And that measure of error will not be anything surprising to us. It's going to be for all of the training data, it's going to be just the average square difference between the data values and our model. Remember, once again, f hat is just our estimate of the model, right? Our estimate of the best model in order to fit that data. And this will be all of our data available to us over all the variables. And so then what we'll do is we'll take the part of the data that we did not use for training, part that was withheld or set aside, and we'll apply it for testing. It'll be our testing data. So we got training data and testing data. And at that point, we can optimize the model hyperparameters. And usually that's related to the degree of complexity of the model. We already have built models that are able to have the best parameters in order to best fit the training data. Now we want to see how the model performs, and we want to test and see if we were overfit. We want to see if maybe we need to prune the model a bit to simplify it a bit in order to have less complexity. And so we're going to test against the available testing data set. And the same way as before, we're going to work with mean squared error or some measure of accuracy of our model. We don't want to ever just go ahead and use all of our data to train the model. First and foremost, we have no way to test the model with cases which were not used to build the model in the first place. We can't really tell how the model is doing if we test it with the same data that we use to train the model. Clearly, if we optimize we're only driven to minimize the difference between the training data and the model itself, we could of course choose a model that's completely overfit, and that would be a problem for using the model on anything besides the training data. There's various different methodologies to conduct this training and testing, splitting, the segmentation of data. One of the most common methodologies would be k-fold cross-validation. And we will have a slide to discuss the jackknife or k-fold cross-validation type of methodologies. So let's talk about decision trees. Decision trees are a machine learning methodology for supervised learning. Going back to a lecture 2 times ago, we were getting into this idea that in machine learning, what we're trying to do is we're trying to estimate a function that can take all of our features. Of course, we acknowledge that there's some error term, some irreducible error that we are unable to capture with the available variables, with the samples that are available to us. But we'll go ahead and take that and we'll try to fit the response model the response with the various features or predictors that are available to us. Of course, these predictors or features are going to be multivariate, where 1 through m different variables are available to us. Now, of course, we talk about right now just one single response. It could be more complicated than that, but for our purposes right now, we keep it pretty simple. And of course, we could work with a continuous response or a categorical response. The continuous response, we would call it a regression tree. Categorical response, we would call it, in fact, a classification tree. So why do we cover decision trees? In fact, if you know something about machine learning, have experienced machine learning before, or you have someone sitting beside you who's sitting there going, Pyrcz is nuts, why is he talking about decision trees? I have method to my madness. The first thing is, of course they're not one of them. They're not really, they're not the most powerful cutting edge method in machine learning. But they are probably the most understandable, interpretable one as far as building what we call a non-parametric, or what I would call a parametric rich machine learning model. Extremely understandable. They also, if you take a decision tree and you expand it with random forest, bagging, or boosting, they can become cutting edge. They can become quite competitive with a lot of the more advanced type of machine learning methodologies. So let's first learn about a single tree, and then we can comprehend the forest. So let's get into decision trees. Let's talk about what we're trying to do with a decision tree. And so the fundamental idea with a decision tree is to divide the predictor space. So if we think about the predictor space, we're thinking about the feature space, we're thinking about all of the variables that we have available in order to make a prediction of the response, variables 1 through m, into j mutually exclusive, exhaustive regions. Well, okay, so why do we say mutually exclusive? For any combination of observed predictors, it will only belong, that one data point will only belong to one single region. The regions cannot overlap with each other. Exhaustive, all combinations of predictors that are possible will belong to a region. The regions cover the entire feature or predictor space. So what we have here is then for every observation in a region, we will then, and the regions will be just denoted as R capital J for the Jth region, we will use the same prediction. That estimate in that region will just be the average of all the values in that region. So for an example, let's take a very simple example. M is equal to 1. We only have one available predictor, porosity, and we're trying to predict production. And for this example, we would then segment this feature space up into 4 regions. Now, I drew them as all kind of equally spaced. They don't have to be, but they're just 4 mutually exclusive, exhaustive regions. 1, 2, 3, 4 regions. Within each one of the regions, we will estimate production as simply being the average of all of the data values, all of the production values within each one of these regions. So you see, that's the idea with decision trees. We just need to segment the feature space up into bins, squares, rectangles, I should say. Of course, in full 3D, in 7D, it doesn't matter the dimensionality. We're going to bin it up into specific regions and then use the average of each region to make a prediction. Now, how do we construct these regions, 1, 2 through J? They could be any shape. In fact, look at this example right here. I have porosity, I have brittleness, and all of the colors here are production. And then so now I have M equals to 2. I have 2 features I'm now working with. So I could actually, if you look at the colors, they're very dark here, high production, lighter here, and then kind of more red right here. So We go from high production to middle, mid-production to low production. I could go ahead and draw these contour lines, and that would be a segmentation of my space, and it would be very efficient. It'd probably be a pretty good predictor. And so that would be something we could do in order to make a prediction. The problem is if we start thinking about that, we think about how to parameterize that problem. It's complicated. We'd have to have in multi-dimensions some type of boundary that is parameterized such that it divides the space. We could do it, and there are methodologies that of course are able to do that type of a segmentation. That's curvilinear and so forth. Support vector machines would be one example of a method that can do that. But we want a methodology that's very simple. We want it to have very easy to understand interpretation and rules, and we want it to be very compact, that the model at the end of the day is a very simple model to understand. So what's the most simple way that we can break up this space into bins or regions that all have very similar productions to each other? And so what we're going to do is we can do this in high dimensional cases. We can use rectangles or boxes, and we can use very simple interpretation rules if we do hierarchical segmentation. So we're going to do hierarchical binary segmentation over the features. It's very flexible, it's very compact, and so this is what it would look like. We could segment this space here by drawing a boundary right here. We could draw another boundary right here, and then we could go ahead and start to break up the other regions, and that's why it's hierarchical binary segmentation. We just keep splitting regions up using very simple straight lines. It's just a rule within each one of the features. Porosity greater than, less than 14 point something percent, or something like that. Okay. So how do we construct the regions? Well, it makes sense to minimize the error. And so what is the error? We'll calculate the error as the residual sum of squares, which would be just simply the sum over all of the, we're going to sum over all of the regions, all of the data within each region, the data values, subtract the average of the region, which is the prediction you would make. That's your estimate within each one of those regions. You do that over all the data, in fact, over all the regions, the data within each one of the regions. And you calculate this residual sum of squares error. And so then what we can do is we can use that and minimize it, place the splits in such a way that we minimize this measure of error. Now, somehow you have to account for complexity. If we just applied this methodology and tried to minimize the residual sum of squares, we would continue dividing, segmenting until every data value was in its own region, and then we'd have no error at all. At that point, we would be clearly overfit, and that would not be a very useful predictive model to take new data and try to make estimates. So how do we account for the cost of complexity? In a little bit, we will talk about the methodology of cross-validation and pruning the tree. So how do we construct these regions? A little bit more on how we get the regions. We want to minimize the error, but how are we going to build it? Well, we're going to do recursive binary splitting. We're going to start with everything in the same region, and then we're going to go ahead and we're going to pick the boundary that we'll move it around. We can move it around. We can move it around on each one of the features. We can move it around on brittleness, moving it up and down. We can move it around on porosity. And we will find the very best split that provides us with the minimum RSS, residual sum of squares, at that point. We're not looking ahead. We're not making any effort to jointly optimize anything. We're greedy. We're short-sighted. We're just every step. How do I do the best job right now? It's top-down because you're going to start with all the data belonging to a single region. And so this is the stem of the tree, the top. I should say it's really like the base of the tree. But anyway, it's the stem, it's the beginning, the trunk. And then you do greedy selection with the single best split over any feature that helps reduce the RSS. Then you can go to the next split and you'll apply the split within any possible region, any possible feature in order to best reduce RSS. So that's all we're doing. How do we construct it? Well, we'll start with one region with all the training data in it. We'll place the region boundary based on a threshold inside this region such that it minimizes RSS. We'll scan over all of the features within all of the regions in order to find that best split. There are, of course, this is not too computationally intense. If you think about it, we only have to look over for each one of the regions, for each one of the features, and we can, of course, there's many ways to scan in a very efficient manner and try to find the best one. So that's not a huge problem. So it can be solved pretty computationally efficiently. And of course, when you apply the new segmentation, you would calculate RSS updating with the new region that's been added. So for instance, if we start with one region and now we're splitting to a second region, we could go ahead and sum the square of the difference of the proposed first region plus the sum of the square of the error within the proposed second region, and we can go ahead very easily and scan across and calculate the RSS for each one of those potential segmentations. So let's pause here and go back to more of our problem where we had a single feature, porosity, and we're trying to predict production. And so let's take what we learned about this idea of segmentation, and let's start with one single region and then try to propose a segmentation on porosity, our one and only feature, in order to minimize the RSS. And so you could put the segmentation at 10%, you could put it at maybe 18%, 14%, 13%. You could put it at different levels of porosity. And when you put it here at 10%, you would now be estimating the whole region with the mean of the data of that region. Region 2 would be the mean of that region. And so you can see very quickly that if I have the division way over here, I'm going to have a huge amount of error with much of the data set. And if I have the bin too far on the other side, I have a lot of error down here. And of course, given that it is a sum of the squares, we would imagine that that would probably have a pretty bad error rate. It'll look pretty poor. So maybe you'll find that something right around here does a pretty good job of minimizing that square difference between the mean and the data values. So this is the first good division to work with. Then what we do is we would, given that first division, well, what we've done is we've actually have our first rule, porosity less than 14.4%, region 1. That's region 1 right here. Porosity greater than 14.4%, region 2. Now what we do is we search over all of the regions. We've got region 1, region 2, and we try to find the next best split. So we scan across in region 1 to try to divide out region 3, scan across in region 2, trying to divide out region 3 over here. And when we do that, we find in fact that this division somewhere right around here does the best job of reducing the RSS. And so this is the very best division that we should use, the best split we should use. And so it turns out to be around 10.1%. And so now in the case that we are less than 14.4%, meaning that this would be our region 1, we're now going to say that we should further split it. If less than 10.1%, we're now going to be region 3, this is region 2, and this would be region 1. And so we're actually building up a decision tree that represents the estimation model, and each one of these nodes at the end, without a decision, would represent a region within our feature space. That's it. We can do this over and over again, and we'll build a tree. Let's take a 2-feature example we have right here. And so for this example right here, we could look at the problem of how do we minimize the RSS. We look at the data. We're trying to predict production given porosity and brittleness now. We have two features we're working with. And so we go ahead and we look at all possible splits on porosity, all possible splits on brittleness. And when we do that, we find that this split right here on porosity is the very best first split. And so what we do is we look at that and we say, okay, that split was around 13.5%. And so in this case, we can say that, all right, we'll say on this side is the case for which we meet that criteria. On this side, the case that we don't meet that criteria. Of course, that could reverse as it did in the previous example. We just have to have a convention and follow it. And so we start to build our tree, and then we could scan even further. And we find that this time in region 2, we could split out and get region 2 if less than 16.3% porosity and region 3 otherwise. And so we now have 3 regions. We've, in a greedy manner, we've now split up the feature space in order to find the best prediction to minimize the RSS, residual sum of squares. Now we keep scanning. Now remember, we're going to scan through all possible regions, all of the regions and all of the features. So every time we scanned through before, we found the very best split was in porosity. Once we got to this point of the tree, when we scan through porosity and we scan through brittleness across all of the regions, we found that dividing region 3 by brittleness now, our first brittleness rule, was the very best thing to do. And so if we carry on, we'll keep subdividing each one of these regions into smaller and smaller regions. This, once again, is hierarchical binary segmentation. It's a recursive method. And so we'll build up a model based on that. Now, of course, it's based on recursive binary splitting, and so the model can't look like that because the splits have to go all the way across the regions. You can't have a split like that. That doesn't make any sense. They have to look like this, that you have a region, split a region, split a region. The splits are all the way across each one of the regions. You don't have a corner like that. But by doing that, we get a very simple model. In fact, at the end of the day, we can visualize our model, and in fact would be a decision tree with the first decision, and then we can further split each one of the regions, split the regions, and so forth, and we'll have terminal nodes with the estimates. And so our model is a nested set of conditional statements in code that we're using in order to make a prediction. In fact, this figure is taken from the James and al. Book that I have referenced in the previous, oh, good, I put a reference there, James and al. 2017, great book. It's actually under my camera right now, so I won't show it to you. So this model, you could build a response surface for it from this decision tree. And so for any combination of each of the two features, you would make a prediction of y, and the model would look like this. It would step. So you're building up your decision tree. How do you stop? How do you decide to terminate or to stop the process of building the tree? And so we make that decision based on a couple of different criteria. Now, the first thing, if we were to go ahead and run until we have every training data value in its own region, this would clearly be overfit. This would be a model that would be perfectly accurate at the training data, but would not be very good for making predictions outside of the training data. Also, if we're overfit, it means that we have a model that's really just capturing the error, the idiosyncrasies of the data, not really the fundamental shapes and forms and that can help us predict from the data. Typical approach is to apply some type of criteria. You could say that I need a minimum number of training data in each one of the regions, in each region. And that would be, basically you're saying I have to calculate an estimate in each region, and I do that as the average. But if I have fewer than 5 training data, can I really calculate an average? Will it not be too noisy? And so that would be your criteria. Another idea is that you just say, well, complexity has a price. If I'm going to accept more complexity, i.e. more branches on my tree, I better be reducing the RSS significantly. And so you put a minimum amount of reduction in the RSS, the residual sum of squares, based on a concept of how much does it cost in order to have more complexity. It better be paid off by reduced error. Now, one thing we've got to be careful about with this type of criteria, if we're too restrictive, we say, wow, you better really reduce that RSS with every single split. There's always the issue that with the current split, you only have a little bit of a reduction, but if you just get past that to another step, you might find another split that now has an opportunity to have even more reduction in the RSS. So you could get stuck early during model construction and miss out on an opportunity to more significantly reduce the RSS or improve the accuracy of your model. Now, excuse me, a grad student just showed up, so I'm back again. Why do we want a less complicated tree? Well, we've already mentioned this. If you allow a tree to grow very complicated, it's clearly overfit, and it's going to be just modeling data error, idiosyncrasies of data, and so this is not useful to us. In addition, there's other considerations. We already mentioned this around this idea of model accuracy and talking about bias and variance trade-offs. And so what do we find in general is that if you have a simpler tree, if you simplify your tree or work with a tree that's less complicated, you do have lower model variance. Your model is more robust in the presence of the available training data. It's not so sensitive. Easier to interpret. You can visualize it, look at it, interrogate it, understand what's going on. Of course, when we simplify our model, we're going to have to accept greater model bias due to the fact that we're using a simple model to try to fit data that may have complicated features to it. Limiting tree growth with a high decrease in RSS required or hurdle can be short-sighted. I mentioned on the previous slide what can happen is you may get stuck at a current step when you could have actually had a better split later on that actually could help you. The best strategy usually is to build a large complicated tree, let it get overgrown, and then prune it. The pruning methodology is we're going to select a subset of the tree that provides the lowest test error. Not training error, but test error now, using data that was not used in order to build the original trees, the original complicated tree. Now, we can't consider all possible sub-trees. That would be too vast of a solution space. But we can definitely try to optimize or fit a variety of different trees on the training data with a variety of degrees of complexity, and then we can test the impact of complexity on estimation or error rate on test data not used originally to build the tree. So in this way, what we're doing is we're training to get the optimum parameters for the tree, and then we're testing to get the optimum hyperparameters. The degree of complexity is a hyperparameter. So let's talk about the overall methodologies. You're going to apply recursive binary splitting to train and grow a large tree. It's overly complicated with the training data. Stop when each terminal node has fewer than a minimum number of data, or you have an insufficient decrease in any one of those steps as far as reduction and residual sum of squared. You obtained a sequence of best subtrees as a function of complexity. Usually that's based on number of terminal nodes. And then you go ahead and you use k-fold cross-validation to choose the best complexity value for the tree, the best complexity or level of complexity in the case of training. You divide the training observations into k-folds, and for each one of them, you go ahead and you build the tree to that level of complexity. You go ahead and test that tree against the withheld data for training, You'll go ahead and repeat that for different levels of complexity. And then what you'll get is you'll have, because you did multiple tests at every level of complexity using the k-folds, you can go ahead and calculate the average error for each one level of complexity. And that's the plot we're going to look at. We're going to look at the plot of average error for each level of complexity, and then we'll decide on which one of those levels of complexity is best for us. Now, let's just, because we mentioned cross-validation, k-fold approach, let's explain in a little bit more detail. The cross-validation approach, you withhold a subset of data during model training. Training is performed with a subset. You have another part of the data that's withheld. Then testing the trained model with the withheld data set is the testing stage. You got to make sure that cross-validation is fair. Sometimes you want to make sure that you didn't just withhold data from a distinctly different part of the data set, because maybe that won't be fair. You're basically testing with something that's completely different from the training data set. So you got training data used for training, testing data withheld for testing. The k-fold approach is a little more efficient, because what you do is you select k. K is going to be some number like 10, 5, 3, and you break the data set into k subsets. You're going to loop over those subsets, and for each one of the iterations, you're going to select a different subset to be testing and the remainder to be training. And so this allows us to repeat the training and testing cycle k times. We can then average the results of the model, the error of the model, over the RSS of the model, over each one of those k attempts, and that provides us a very nice measure of the performance of the model. In fact, we can plot that against the degree of complexity of the model and get a very good sense of as far as the model performance versus complexity. And we'll do that. And don't worry about all that loop iteration, because this is something that's basically already put together for us within code. It runs very efficiently for us. So let's go ahead and go to our unconventional data set. It's a multivariate data set that's ready for us to work with. That data set is available on GitHub. It was mentioned and discussed in the previous lecture on principal component analysis. And so we are going to specifically look at the production variable. For a prediction problem, we're going to do a regression tree. We're going to use both porosity and brittleness in order to get to production. They have kind of an interesting relationship. If you look at the relationship between production and porosity, it's monotonically increasing. There's this really nice shape right here, plus it's heteroscedastic. It has increasing variability in production as we go to higher porosity values. Brittleness, interesting. There's clearly a sweet spot of brittleness, and then we get poorer production out here towards the extremes or the tails of brittleness. All right, so we can work with those. Let's go ahead and look at the relationship in really three-dimensional. And so we'll look at the porosity, brittleness versus production. This is for the available data for us. And so we can go ahead and look at the overall relationship. And you can see there's an interesting structure here, higher production right here. The darker colors are higher, lower going like this. So there's a radial pattern. There's also a region here where we have not sampled. Those combinations of the features just don't exist. And then we can go ahead and extract a training data set that we're going to work with. We could extract a small set. Depending on the methodology we want to work with, we could work with 100, 400, we could do k-fold or whatever we want to do. But for now, we're just going to demonstrate taking a subset of the data, as training, and training ourselves a model. We're going to build an initial, reasonably complicated tree to work with. Well, it seems pretty reasonable to say that a minimum number of data at each terminal node, or in other words, in each region, should be 10 data. That should give us a pretty reasonable estimate of the mean within each one of those regions. We can go ahead and run that tree in R. And if we do that, we'll get output that tells us about the model. It's going to tell us specifically the number of terminal nodes, which is the number of regions. And so that's useful. That's a good number to represent the complexity of our tree. It's going to provide a variety of summary statistics. The sum is squared, the residual sum is squares, and so we can get a sense of what's going on as far as the amount of error overall reported to us. We can also see statistics such as the distribution of the residuals. And so what do we expect to see? Well, we'd want to see a symmetric error, that we don't have, the mean should be equal close to 0, indicating that our tree is not biased, and that we want to see the overall range of error, that it's not too large. We could plot up the error distributions too, of course. We can also, the overall quality of the model is reported as residual mean deviance, which is really just the total residual deviance divided by the number of observations minus the number of terminal nodes. And so this calculation, for this calculation, it uses the total residual deviance, which in this case is really equal to the RSS, which we've already talked about before. The only thing is that we're standardizing it by the number of observations or data minus the number of terminal nodes. So just a correction here, I noticed that I've actually trained this data with 500 data, and we have 10 nodes we're working with here. Okay, so far so good. Here's the tree. One of the best things about decision trees, you can visualize it. You can look at it and see exactly what it looks like. And it's no surprise. We have our first split, and then for each of the regions, so region 1, region 2, or whatever they might be, then region 1 and region 3, region 2 and region 4, whatever the numbering is, we continue to split into multiple regions. Another thing that's interesting to see is that we have to get 3 decisions in before we see brittleness show up. So it shows us that porosity is really the most important feature when it comes to making a prediction in production. The other thing that indicates that to us is that the length of the branches is proportional to the decrease in RSS in the model for each one of those splits. So this split right here resulted in this length of these branches right here. You can see that that decision is the most important. It had the biggest impact on RSS, and then this split right here basically only added a decrease of about maybe 1/3 or 1/4 what we got from the first choice. This one maybe 1/5, 1/6, 1/7. It's not, and by the time we get out to these nodes right here, or these last choices right here, they're little twigs. The lengths of those arms are so short because there's very little improvement in RSS or decrease in RSS through making those choices. Okay, so that's what the tree looked like if you just look at the tree as far as the choices, the splits. If you have a two-dimensional, or if you have features which are just 2D or 1D, you can of course look at the feature space and you can plot these segmentations like I did before when I was describing the building of a tree. And then it'll even plot, in R it does this very nicely, it will plot the actual values being used to estimate, which would be the average of the data within each one of these regions. And you can get a sense of what's going on as far as the overall tree. How's it looking for us? And so if we do that, we can get a sense of what our predictive model is doing. How is it calculated, the tree? These are just a bunch of conditional statements to be able to get to the estimate at the nodes or the ends of the branches. And then what our model looks like with regard to all the possible answers from the feature space, we can see the segmentation right here. So we're going to build an initially reasonably complicated tree, and then we perform k-fold cross-validation. And if we do that, we will get over the k-folds an average amount of error for each level of complexity. What happens if we take our original tree of 12 nodes and we prune it, train and test it, prune it, we test it, test it, all the way back? What happens as far as the overall error in making predictions when we have different levels of complexity. From that, we can make a choice about how complicated a tree should we be working with. And so if we do that, how do we make a choice? Well, this is the plot right here. RSS for 1 node, 2 nodes, 3 nodes, 4 nodes, and on. How would we make a choice? Well, the first thing you could do is you could say, well, I need my tree to get down to a certain acceptable level of error. And I will accept any level of complexity to get me to that level of error. And so if you do that, you'd say something like 10 nodes are required to get to that acceptable error. Another thing you could do is you could look at the diminishing returns. You could say, well, every additional node is more complexity. I need to significantly decrease RSS, and I won't accept complexity that has diminishing returns. It has too little payoff in decreased RSS. I'd rather have simplicity. So you could calculate a slope right here. You calculate a slope right here, and you could say, right here is an inflection point. There's just too little decrease in RSS from here on in. I'm going to say 6 nodes, not 10 nodes. Now, of course, that's subjective. You could also pick right here, because right here at 9 nodes, clearly you're having very little incremental improvement, whereas here you had more. So you'd have to make a choice exactly what's acceptable level, what's the required rate of improvement, and you can make a choice. Well, if you make a choice to prune it back to 1, 2, 3, 4, 5, 6 nodes, you get 6 regions now. So we took that original tree and we pruned it back, and this is the model we now have. The unpruned original tree, the pruned tree, so this has 12 nodes, 12 regions, 6 regions, and that's the resulting model. And we can go ahead and try to do some type of cross-validation with the testing data set. We can just check and see how our predictions look. And so this is the predictions we'd make. This is the true values in the testing data set for production. And what do we see? Is there any surprise here? Well, you can see overall that we have only 6 possible values for our predictions. And that makes sense. We only have 6 regions. For any combinations of the features, we can only predict with those 6 values, the averages over each one of those regions. The model looks pretty good. We show this plot right here to look at the result as far as the predictions versus the truth, but of course there's lots of different statistics we could look at. We could look at the RSS of the model and describe that. We could look at if there's bias in the model. As we mentioned before, you can check the mean of the errors. We could look at the spread of the errors to see if they're symmetric. There's other things we could do to test the model. So the example I just showed you was in R. Now, I'm in love with R. I think R is great as a teaching tool and to use in research. The methods are very robust, but I also very much like Python. So I'm a little bit divided on that. And scikit-learn provides a lot of really great tools for doing machine learning. And so there is a Python workflow that takes the same data, does some initial data analysis, then it goes ahead and builds different decision trees. It visualizes the decision tree within the feature space like we did before. It then goes ahead and it does a k-fold cross-validation to get the right level of complexity, and we make a choice based on that. We prune ourselves down to this tree right here from this tree right here that was too complicated and was probably overfit. So that workflow is available to you on my GitHub account, Geostat Guy on GitHub. I have a repository which has Python numerical demos, and within that repository there is this decision tree workflow. So you'll find that it goes through the data. There's some subroutines that are put together for the purpose of visualizing the decision trees, and I give credit to a variety of different authors who provided these excellent subroutines for investigating decision trees. Data display, there's a little bit of data cleanup, looking at the relationships between all of the variables. We go ahead and work with production and brittleness again, look at their distributions, plot their relationships, and we build a decision tree. We can cross-validate that, see how we do as far as prediction with regard to our decision tree. We can visualize the decision tree, and then we can run cross-validation where we vary the degree of complexity of the decision tree. Here's some example decision trees with different degrees of complexity. And we can go ahead and plot decision tree error. The mean squared error is shown here. MSE, well, of course, there is, previously we were looking at the residual sum of squares. Doesn't matter. It's a measure of error, summarization of error. And from that, we can go ahead and pick an optimum tree to work with, based maybe on a acceptable level of error, or maybe based on an inflection point, a concept of diminishing returns. And from that, we're able to go ahead and prune our tree, and this would be a resulting tree that we could work with. The cool thing too is you could also convert your tree into code. And if you do that, and that was provided with a subroutine that's very useful, you'll find that your decision tree, based on porosity and brittleness, is just going to be a set of nested conditional statements. So you can go ahead and for each one of the thresholds from your decision tree, you make a prediction, and these returns are going to be the prediction in each one of the regions as you go recursively down through your decision tree to the final region. This visualization method is very cool. We can look at the actual decision tree, and it tells us the residual sum of squares if we were to stop the tree at each one of the nodes. It tells us what the estimates would be at each node and the decision criteria for the nodes. Okay, so this is the Python code and workflow that's available to you on GitHub if you want to check it out in Python 2. Okay, so some final comments as far as decision trees. Okay, why did we show you decision trees? They're easy to explain. Some would even suggest that they are analogous to the way that we make decisions. That this type of binary segmentation, a recursive binary segmentation, is something we do in our heads to make choices with complicated problems. That's kind of cool. Graphically, you can look at them. They're very cool that way. You can look at the decision tree. You can work continuous or categorical variables with either a regression tree or with a classification tree. They have lower accuracy than other machine learning methods. The model variance, the model bias, in fact, may be in fact high because it's kind of a simple model. So you might think, well, we need a more complicated model to fit more complicated situations. Well, as I mentioned before, once you know about decision trees, you can go higher tech. You can do more complicated things. All of the following methods are around how do you improve the accuracy of a decision tree. Bagging, the first methodology we'll mention. We use Bootstrap on the training data set to get B training sets, multiple realizations of the training set. You train the tree with each one of those bootstrapped data sets. You then use all the models and you average the result to get a prediction. So you have your multiple trees by using bagging, bootstrap resampling of the data. You use each one of those trees, which are going to be modeled, in order to, or trained I should say, to make the prediction. And then you take the average of all the predictions from the B different trees. Now what's cool about this is you can let the trees grow large. You can get them, they can be overgrown. But what you'll do is, now that these trees are overfit to the bootstrap data, you'll build hundreds or thousands of trees, a forest of okay estimates. They're not going to be great estimates, but they're going to be okay. And so then what you do is, if you're doing classification, you'll take the majority rule. If you're doing regression, you'll take the average, as we show in this equation right here. The other thing that's very cool about this is every time you build a tree, you're bootstrap sampling. And so with the bootstrap, there's going to be samples that are not included to build the tree. That means that with every tree, you have some data left out that can be used for testing. And so testing your model can occur during the process of building the model, and that can be reported to you to understand how your model is performing. Another methodology is random forest. Same as bagging. Start with the idea of bootstrap samples of data, but we're also going to bootstrap or randomly select about a subset of the variables. So we have m variables. We'll typically take the square root of m. If we have 9 variables, we'll retain 3 variables on every one of the trees. So we're only going to work with 3 features, not the full 9 features if we had 9, and so forth. What does this do for us? Now we're going to prevent a single strong predictor from dominating the entire set of trees. We're forcing diversity among our trees. We're decorrelating the trees. So this is very interesting because by improving the diversity of the trees, we find this method actually is more powerful. It provides a better estimate at the end. And we're going to do what we did before. We're going to have a bunch of trees, and we can take the average for regression, or we can take the majority rule for classification. What's the idea of boosting? Boosting, you're going to sequentially model simple trees. You're going to build a tree, a very simple tree, calculate a residual. The residual is the error of your prediction. Then you're going to model another simple tree, but you're going to model it on using you're going to fit the residual with that second tree. Then a third tree is going to fit the residual from the second tree. So in fact what you're doing is you're recursively modeling the error, fitting the error to correct for it, and then you try again. You'll test that and you'll find that there's more error, and you go ahead and fit that. And you can do that over and over again. And the result of boosting is that you get, instead of the idea of a forest of kind of not very smart trees that do very well together, this idea is that you stack the trees on top of each other and have them all help each other directly make the single estimate. One capturing first kind of not a great estimate, the second one taking that estimate, improving it, improving it, improving it, improving it. So that is the end of our discussion on decision trees. I hope this was useful to you. I like decision trees. For machine learning, I do believe it's one of the most simplest non-parametric approaches for the purpose of prediction. It's very easy to interrogate. It's very visual. I hope you agree. I hope this was useful. Feel free to check out the R and the Python examples. They're both available. DT_demo on my GitHub repository, within my Geostat R repository, I should say, and within my Python numerical demos repositories. They're available to you. The data sets are also available. They're indicated within the code. All right, I'm always happy to answer questions. You can reach me. I'm available on Twitter. You can DM me. I am the Geostat. I'm the Geostats guy. And I'm also a professor here at the University of Texas at Austin. And I'm super easy to find. You can get my contacts. Go ahead, email me or whatever. All right. Take care.